So now let's look at how we can put everything together and use the principles of the virtual work um, to calculate the stiffness matrix elements for a typical finite element that we use in the finite element analysis. Now, the mathematical form of the final matrix elements, for example, in this case, the triangular matrix element is written in the slides 78. So the final form of the K matrix is on slide 78. Now, you actually don't need to really know or remember the matrix for um, all the terms for this matrix element because it's quite complicated. And in reality, this is done by a computer. They'll all be calculated for you. But we just need to go through the whole process or the mathematical derivation to see how you might get there in a sort of practical setting or board and pen methods. So just a brief recap from the principle of virtual work of virtual work. We know that the K is driven by what? B transpose times D times B. Okay? Where the B matrix itself, B is S dot N. Right? We just work out the N the shape function matrix. We know how to work that out. The S matrix, as we shown before, is a differential operator, d by dx, 0, 0 d by dx, dy, and d by dx, d by dy. Right? And the D matrix is related to the mechanical property of the finite element or the material we are using, and we know that D is equal to what? E over 1 minus mu square times 1 mu 0 mu 1 0 1 minus mu over 2, right? Where E is the Young's modulus and V or the mu is the Poisson ratio, okay? Now, if you look at here, it's quite straightforward to work out K from D and B. Basically, you just need to do a matrix product, right? We know the D matrix, and provided if we know the B matrix, we can work out the value of K. Now, how do we work out B? This is actually the challenging part, and that's what we're going to show in this video, okay? The rest of this is basically pure algebra, okay? So now we know that the shape function for triangular element, the shape function for triangular element is a 2 by 6 matrix. So we write that as n 2 times 6. And if you recall the slides before, n take this form of n1 0, n2 0, and 3 0, right? And 0 and 1, 0 and 2, and 0 and 3, right? So what are these? Well, before we go into more details, right? If we have S, which is in this case a 3 by 2 matrix, and N is 2 by 6 matrix, what we're going to get out is what? Is this B matrix, which will be given by this 3 and 6, because all these 2 got condensed in the matrix operation. So B will be a 3 by 6 matrix. So B will look something like this. So we will have 3 rows and 6 columns. So 3 rows, 1, 2, and 3. And one of these columns, so there are 6 columns, okay? Right? So we need to work out each one of those, right? So for example, this is matrix element 1, 1. So what would be B1, 1, right? We know that from the matrix operation, or the matrix product, this will be given by the first row of x times with first column of s times n, this big N, right as this big N, which is this guy, the first row and first column of the matrix element for N. So basically here is this times this, and sum it together, so is, and the next term will be S to 2 dot, sorry, S 1, 2 times N 1, 2. So remember, if we have this notation, we have the row index followed by the column index, right? Now I can't actually do the dot product because here x is actually a differential operator. So what does that mean? What's S11 in this case? Well, first row, first column, that's what? D by dx. So we have d by dx, right? I don't know what N11 is, so I leave there. And S12 is first row, second column, which is 0, so that gives me 0, right? Which we can just ignore that. So B11, this first matrix element is what? D by dx N11, right? And what's this N11? So if we go back to the derivation we have a couple of slides ago, right? We have this N, and N11 is basically what? N1, right? N11 is this guy, is basically N1. And N1 is what? We had previously the definition where NA equal to A sub A plus B sub AX plus C sub A Y over 2 delta, where A equal to 1, 2, or 3. Now, we want A1, so when A equal to 1, we have AA equal to what? X2, Y3 minus X3, Y2, right? These are basically the relationship between the coordinates for the nodes. We have BA equal to y2 minus y3, and C of A equal to what? x3 minus x2, right? So if you plot that, so you notice here, all the A, B, and C, they have x and y with a number or numeric substrate. So what that means, these are basically constants, right? That depends on the positions of your nodes. So those are the constants. So if they are constants, how can we do a differential operator on constants, which is give you 0? But that's not the case. As you can see here, this is a shape function that interpolates an arbitrary point between all the nodes. So we have this x here and y here. That means we can actually differentiate this d by dx and 1, which is d by dx times 2 delta at the bottom, a plus bax plus cay, right? We know how to do differentiate of a linear function. That basically gives us back the coefficient in front of x, right? So b11 is equal to 1 over 2 delta times ba. What's ba? Is this guy here. So b11 equal to 1 over 2 delta y2 o minus y3. Right? That's how we work out one of the matrix element for B, which is this guy here. Right? We work out this guy, which is this. Right? Now if you go through the whole procedure, you'll be able to work out the whole matrix, which I write in a sticker pen. We can work out the whole B matrix, right? This is given in your slides 77. So here is in slides 77. And that looks like this. 1 over 2 delta. Of course, you don't need to remember that. That's something down in the computer. We have y2 minus y3 goes in here, and we have 0, y3 minus y1. Basically, you need to differentiate all these shape function term by term, element by element. 0, y1 minus y2, 0, 0, x2 minus x3, 0, x1 minus x3, 0, x2 minus x1, x3 minus x2, 0, oh sorry, this is y2 minus y3, x1 minus x3, y3 minus y1, x2 minus x1, there's a typo in the notes, and y1 minus y2, right? So basically, if you look at this, now what does this B tells us, right? Basically, this B matrix, right, is telling us, right, the what we call is internal coordinate. Now you can actually see this B matrix in many other fields, like even the field I work with is quantum chemistry. We have this B matrix that look at how a molecule will deform as it vibrates. This also applies to solids, etc. And all this information goes in here are the internal coordinates for the shape of the finite element. Right? What does that mean? So if you look at a triangle, well, you have 1, 2, and 3 in this Cartesian frame x and y, right? This term y2 minus y3, what does that mean? That's the y coordinate of 2 and 3, and the difference between the two is basically the length of this side being projected onto the y-axis, right? So this is basically tells you the change. Somewhat is related to the change of the nodes, right? The finite difference of the nodes when it deforms, and how that is related to the internal coordinate or the bonding, right? The mechanical interactions between the two nodes. So this is the information that goes into the B matrix, right? So once you got the B matrix, we now have the B matrix. We also have the D matrix. As we shown before, all we want to do is basically work out what's BT dot D dot B. Right? That's our K, the final stiffness matrix element, which is a long, really long matrix that's written on slides 78, which you can look at in your lecture slide to just get a flavor how this thing look like in real world. Now, if you don't have my slide, for example, you watching this video on YouTube, you can basically find out the expression for standard triangular matrix element in many textbooks of finite element analysis. Now, if you know the basic principle of how to work out this B matrix, now in the last few slides of this course, we basically work out the go through the same procedure for a rectangular matrix, rectangular finite element. So in the final part, we have a rectangular finite element, right? And the whole procedure is basically the same thing. We have, in this case, the N shape matrix is a 2 by 8 matrix that we worked out before. So we have something that look like N1, 0, N2, 0, N3, 0, N4, 0, and 0, and 1, and 5, 0, and 6, 0, and 7, and 0, and 8. Well, we have the expression for each of the term worked out in the previous few slides. So let's actually